You live in a world that feels solid, predictable, and easy to understand at everyday scale. You drop a ball and it falls. You switch on a light and it turns on. You drive a car and it follows a clear path. Your daily experience teaches you that the universe behaves in a stable and logical way. That view works beautifully for most things you do in life. But when you move into the world of atoms, electrons, photons, and the very smallest building blocks of nature, the rules begin to look very different. This is where quantum physics begins. Quantum physics is the branch of science that helps you understand how nature behaves at extremely small scales. It explains why energy comes in packets, why particles can behave like waves, why observation matters, and why certainty becomes more limited than you might expect. At first, this can sound strange, confusing, or even impossible. But quantum physics is not magic. It is a real and tested way of describing how the microscopic world works. And if you want to understand quantum computing properly, you need to understand these ideas first, because quantum computers are built on these unusual rules rather than on ordinary everyday logic. Quantum physics helps you see the hidden rules of the microscopic world, and those rules are the foundation of quantum computing. You might wonder why you should care about quantum physics at all. After all, most people are not planning to become physicists. But quantum physics matters because it is already shaping the technologies around you. Modern electronics, lasers, semiconductors, magnetic resonance imaging, solar cells, and many communication technologies rely on ideas that came from quantum physics. Even if you never use the word quantum in your normal life, the results of quantum science are already part of your world. Quantum computing takes this one step further. A classical computer works using bits that are either 0 or 1. A quantum computer works using quantum systems that follow the laws of quantum physics. That means if you want to understand why a quantum computer is different, more powerful for some tasks and harder to build, you first need a simple but strong understanding of the physics behind it. Without that foundation, quantum computing can sound like hype. With that foundation, it starts to make sense. Quantum physics matters because it explains both the strange behavior of nature and the technology behind quantum computing. Before quantum physics emerged, scientists had great success using classical physics. Classical physics, shaped by thinkers such as Isaac Newton, helped explain motion, force, gravity, heat, and light in many situations. It gave people enormous confidence that the universe could be understood as a machine with clear rules. If you knew the starting conditions, you could predict what would happen next. This way of thinking worked very well for planets, projectiles, engines, and large objects. But as scientists began studying light, atoms, and very small particles more closely, classical physics started to struggle. Some experiments produced results that did not fit the old model. Light sometimes behaved in unexpected ways. Energy did not seem to flow in a smooth and continuous manner in every case. Atoms behaved more like tiny structured systems than classical physics could properly explain. It became clear that the old rules were powerful, but they were not enough. Quantum physics was born because classical physics could not fully explain the behavior of the microscopic world. One of the earliest breakthroughs came when scientists studied how hot objects glow. Classical physics could not correctly explain the energy pattern of this glow, which became known as blackbody radiation. To solve the problem, Max Planck proposed something radical. He suggested that energy is not always exchanged smoothly, like water flowing from a tap. Instead, it can come in tiny discrete packets. These packets later became known as quanta. This idea was a turning point. It meant nature might not be perfectly continuous at microscopic scales. So a little later, Albert Einstein extended this thinking when explaining the photoelectric effect. He showed that light could behave as if it came in packets of energy called photons. This was a huge shift. Light, which many people thought of only as a wave, also seemed to act like a particle in some situations. That was one of the first strong signs that the microscopic world does not fit neatly into ordinary categories. Quantum physics began when scientists realized that energy and light behave in discrete and surprising ways at very small scales. The word quantum can sound mysterious, but the basic idea is simple. A quantum is the smallest meaningful packet of something in a physical process. In many quantum situations, energy is not divided into any amount you want. Instead, it appears in specific allowed amounts. You can think of it like stairs instead of a smooth ramp. On a ramp, you can stand anywhere. On stairs, you stand on one step or another step. In a similar way, certain physical systems allow only specific energy values. This was a major change in thinking because it told you that the microscopic world has built-in structure. Electrons in atoms do not sit at just any energy level. They occupy specific levels. When they move between levels, they absorb or release exact amounts of energy. This is one reason atoms emit very specific colors of light. The quantum idea is not just about smallness. It is about nature allowing certain values and not others. A quantum is a discrete packet, and this idea helps explain why microscopic systems behave in structured, not continuous ways. One of the strangest ideas in quantum physics is wave-particle duality. In simple terms, some things that seem like particles can also behave like waves, and some things that seem like waves can also behave like particles. Light is the classic example. In some experiments, light behaves like a wave, spreading out and creating interference patterns. In other experiments, it behaves like packets of energy called photons. Even more surprising, matter itself can behave this way. Electrons, which you might imagine as tiny particles, can also show wave-like behavior. This means that the smallest building blocks of nature do not fit neatly into your usual categories. They are not just little balls and not just ripples either. Their behavior depends on how you study them and what kind of interaction is taking place. This matters deeply for quantum computing because quantum systems are not forced into simple everyday identities. Their unusual behavior makes new forms of information processing possible. In the quantum world, particles and waves are not opposites. They are two ways microscopic systems can reveal themselves. If you want one experiment that captures the strange beauty of quantum physics, the double-slit experiment is a powerful choice. Imagine sending light or electrons toward a barrier with two narrow openings and observing what appears on a screen behind it. If you think only in classical terms, you would expect particles to go through one slit or the other and create two bands on the screen. But what actually appears is an interference pattern, the kind you expect from waves overlapping. The shock becomes even greater when particles are sent one at a time. You might think each particle should simply choose one path. Yet over time, the same interference pattern still builds up. It is as if each particle behaves like a wave of possibilities while moving and then appears as the localized event when detected. When scientists try to measure exactly which slit the particle goes through, the interference pattern changes or disappears. This tells you that the act of observation is not a passive event. It changes what happens. The double-slit experiment shows you that quantum behavior is based on possibilities, probabilities, and measurement, not simple everyday paths. Now you reach one of the most important ideas in both quantum physics and quantum computing: superposition. In simple language, superposition means a quantum system can exist in multiple possible states at the same time until a measurement is made. This does not mean the system is confused. It means nature allows a richer form of description than ordinary either-or thinking. A classical bit in a computer is either 0 or 1. A quantum bit, often called a qubit, can exist in a superposition of 0 and 1. This does not mean you read both values in the ordinary sense whenever you want. It means the system carries a combination of possibilities that can evolve according to quantum rules. That is one reason quantum computing is so different. It does not simply use smaller switches. It uses systems that behave according to quantum superposition. If you do not understand superposition, quantum computing will always sound mysterious. Once you understand it, you begin to see why quantum systems can process information in ways that classical systems cannot easily copy. Superposition is the idea that gives quantum systems their rich behavior and gives quantum computing its unusual potential. In classical thinking, you often expect physics to tell you exactly what will happen. In quantum physics, the theory often tells you the probability of different outcomes rather than one guaranteed result. Before measurement, a quantum system is described by a spread of possibilities. When measurement happens, you observe one outcome from those possibilities. This does not mean quantum physics is random in a careless or meaningless way. It means the theory is built around probabilities at a fundamental level. You can predict patterns extremely accurately across many repeated experiments, but you may not predict the exact single outcome every time in the same classical way. This shift from certainty to probability is one of the hardest parts for beginners to accept because everyday life trains you to expect definite answers. For quantum computing, this matters because reading a qubit is not like reading a normal switch. Measurement affects the system. The result you get is tied to the probabilities built into the quantum state. That is why designing quantum algorithms is not just about storing information. It is also about shaping probabilities so that useful answers become more likely. Quantum physics replaces simple certainty with probability, and that shift is central to how quantum computers work. Another famous idea in quantum physics is the Heisenberg uncertainty principle. People often misunderstand this idea and think it means science is sloppy or that measurement tools are weak. That is not the point. The uncertainty principle tells you that certain pairs of properties such as position and momentum cannot both be known with unlimited precision at the same time. This is not just a technical limitation. It is built into the structure of quantum theory. If you try to pin down a particle's exact position very sharply, you lose precision about its momentum. If you know momentum very precisely, position becomes less definite. This does not mean particles are hiding information from you like a puzzle game. It means quantum systems do not always possess classical style exactness for all properties simultaneously. This matters for quantum computing because control at the quantum level is delicate. You are not working with little metal balls that sit neatly in place. You are working with systems that must be prepared, isolated, and measured under rules that are more subtle than ordinary engineering. The uncertainty principle reminds you that the microscopic world is governed by limits built into nature itself. To understand quantum computing more deeply, you need to become comfortable with the idea of a quantum state. A quantum state is the full description of a quantum system according to quantum theory. It contains the information needed to calculate what outcomes are possible and how likely they are. You do not need advanced mathematics to grasp the spirit of it. Think of a quantum state as the complete set of possibilities available to the system at a given moment. This state evolves over time according to quantum rules. When no measurement interferes, the evolution can be smooth and predictable in a mathematical sense. But when measurement occurs, You observe a definite result from the available possibilities. This mix of structured evolution and probabilistic outcome is part of what makes quantum theory so powerful and so strange. Quantum computing works by carefully preparing quantum states, transforming them through operations, and then measuring them in ways that reveal useful information. That is why understanding the idea of a quantum state is not optional if you want to go beyond surface level explanations. A quantum state is the language of possibility, and quantum computing depends on creating and controlling those possibilities. Entanglement is one of the most fascinating and important ideas in quantum physics. When two quantum systems become entangled, their properties become linked in a way that cannot be fully described as separate independent parts. Measuring one system gives you information about the other, even when they are separated by large distances. This does not mean ordinary communication is happening instantly in the way movies often suggest. It means the systems share a deeper quantum relationship. Albert Einstein found this idea uncomfortable and famously criticized aspects of it. But experiments have repeatedly shown that entanglement is real. It is not just a philosophical curiosity. It is a usable feature of the quantum world. This makes it incredibly important for quantum information science. In quantum computing, entanglement allows qubits to be connected in ways that classical bits cannot match. It helps create coordinated quantum states that support powerful computation, quantum communication, and quantum cryptography. Without entanglement, much of the excitement around quantum computing would disappear. Entanglement is a uniquely quantum connection, and it is one of the main reasons quantum computing can do things classical systems struggle to imitate. Now, it helps to ground the discussion in physical systems you can imagine more easily. Atoms are made of a small nucleus and electrons that occupy allowed energy levels. These electrons do not move like tiny planets orbiting in a simple classical way. Instead, they exist in quantum states. They occupy specific allowed patterns and energy levels around the nucleus. When an electron changes from one level to another, it absorbs or emits a specific amount of energy. That is why atomic systems produce characteristic patterns of light. These energy levels, transitions, and quantum states are not only central to physics, they are also useful in building quantum technologies. Many quantum computing platforms use controlled quantum states in atoms, ions, superconducting circuits, or other systems to create qubits. So when you learn about electrons, levels, transitions, and quantum states in atoms, you are not just learning old textbook science. You are learning the kind of physical behavior engineers and scientists use when they try to build real quantum computers. Quantum computing depends on real physical quantum systems, and atoms help you understand how those systems behave. At this point, you can start connecting physics to computing more directly. Traditional computing is built on bits, logic gates, electrical signals, and transistor-based switching. Quantum computing builds on quantum states, superposition, entanglement, and measurement. The move from quantum physics to quantum information is the move from understanding nature to using nature for information processing. In classical computing, information is encoded in definite states. In quantum computing, information is encoded in quantum states. This means operations are not just ordinary logical flips. They are controlled transformations of quantum systems. The aim is not to copy a normal computer with exotic hardware. The aim is to exploit the real behavior of quantum systems to solve certain problems more effectively. This is why quantum physics is necessary for quantum computing. If you remove the physics, the computer loses its quantum advantage. Superposition, interference, and entanglement are not decorative ideas. They are the reason the machine is quantum at all. Quantum computing is not separate from quantum physics. It is Quantum physics turned into information processing. A qubit is the quantum version of a bit, but it is much more than a smaller bit. A classical bit is either 0 or 1. A qubit can exist in a quantum combination of 0 and 1 until measured. This is possible because the qubit is a real quantum system, such as an electron spin, an ion state, or a superconducting circuit state. When you first hear this, it is tempting to think a qubit is simply both 0 and 1 in a magical way. A better way to think about it is that a qubit carries a state that includes both possibilities, and quantum operations can manipulate that state before measurement. When many qubits are combined, the space of possible states grows very quickly. That is part of what gives quantum computing its potential power. But qubits are also fragile. Noise, heat, vibration, and unwanted interaction with the environment can damage their quantum behavior. That is why building useful quantum computers is so difficult. The same physics that gives qubits their power also makes them delicate. A qubit is a controlled quantum system whose unusual state behavior makes quantum computing possible. Interference is another key idea that connects quantum physics to quantum computing. In wave behavior, waves can combine to strengthen each other or weaken each other. Quantum states can do something similar. Because probability amplitudes behave like waves in important ways, quantum processes can be designed so that unwanted possibilities cancel out while useful possibilities become stronger. This is one of the secrets behind famous quantum algorithms. The computer is not simply trying all answers in a crude way. Instead, it uses quantum evolution to shape the pattern of possibilities. Through interference, the algorithm increases the chance that the correct or useful answer will appear when measurement happens. Without understanding interference, you might imagine quantum computing as just many answers at once. That is incomplete. The real power comes from how those possibilities are guided, combined, and filtered through quantum operations before the final measurement. Interference is how quantum algorithms shape probability so that useful outcomes become more likely. By now, quantum computing may sound exciting, but you should also understand why it is so hard to build. Quantum systems are fragile. They are easily disturbed by their environment. Any unwanted interaction with heat, electromagnetic noise, vibration, material defects, or measurement like disturbance can damage the quantum state. This loss of fragile quantum behavior is often called decoherence. Scientists and engineers must keep qubits stable long enough to perform useful operations. They also need to control qubits with precision, connect them properly, read them accurately, and correct errors that occur along the way. This is very different from ordinary digital engineering. Classical computers also face noise and hardware issues, but quantum systems face deeper challenges because they depend on preserving delicate microscopic behavior. That is why quantum computing is not just a software revolution. It is also a physics and engineering challenge of the highest order. To build better quantum computers, you need people who understand both the abstract theory and the physical reality of quantum systems. Quantum computing is difficult because the same quantum behavior that gives power also creates fragility. As you learn quantum physics, it is helpful to avoid a few common mistakes. The first mistake is to think quantum means magical. It does not. Quantum physics is unusual, but it is still a rigorous science tested by experiment. The second mistake is to think quantum computers will replace all classical computers. They will not. Classical computers remain better for many everyday tasks. Quantum computers are promising for specific kinds of problems, not for everything. Another mistake is to think quantum physics only matters in laboratories. In reality, it already shapes many modern technologies. One more mistake is to think you must understand advanced mathematics before you can understand the ideas. The mathematics is essential for deep mastery, but the conceptual foundations can absolutely be understood in clear language first. That is the right starting point for beginners. If you stay grounded, curious, and patient, quantum physics becomes much more approachable. The subject is strange, but it is not beyond you. Quantum physics becomes easier when you stop treating it as magic and start treating it as a new set of rules for the microscopic world. A good beginner to advanced understanding of quantum physics does not mean you can instantly solve difficult equations or design a quantum processor from scratch. It means you understand the major ideas clearly. You know that quantum physics describes the microscopic world. You understand quanta, wave-particle duality, superposition, probability, measurement, uncertainty, quantum states, entanglement, and interference. You also understand that these ideas are not philosophical decorations. They are the real foundations of quantum computing. When your understanding becomes stronger, quantum computing stops sounding like a mysterious black box. You begin to see why qubits are different from bits, why measurement matters, why entanglement matters, why interference matters, and why engineering a quantum computer is so difficult. That is the point where you move from curiosity into meaningful understanding. This is the mindset you want to keep. Do not rush. Build your foundation properly. The deeper your understanding of quantum physics, the clearer your understanding of quantum computing will become. A strong understanding of quantum physics turns quantum computing from hype into something you can genuinely follow and explain. As you step back from everything you learned, remember this simple truth. Quantum physics is not just an advanced topic for scientists. It is the language nature uses at the smallest scales, and it is the foundation on which quantum computing is built. If you want to understand quantum computers in a serious and meaningful way, you cannot skip the physics. You need to understand why the microscopic world behaves differently, why probability matters, why superposition and entanglement matter, and why controlling these effects is both powerful and difficult. So, as you continue your learning journey, do not be intimidated by the word quantum. Start with the ideas. Build your confidence step by step. Stay curious about how nature behaves beneath the surface of everyday life. Because once you understand that hidden world a little better, you will also understand why quantum computing is one of the most important technological frontiers of your time. If this session helped you understand quantum physics in a simple and practical way, subscribe to the channel, like the video, and share it with others who want to explore the future of science and computing with clarity rather than confusion. Leave a comment and share which concept changed your understanding the most. Your learning may help someone else begin their journey too. Quantum physics is the foundation, and understanding it is the key to understanding quantum computing.